This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel for further selected topics. This video is about clause 9 and it deals with the serviceability limit state, and we will start off with stress and crack control. We compare Eurocode 2 version 2023 with Eurocode 2 version 2004. You will see that in the version of 2023, stress limitation and crack control is grouped together in clause 9.2, but the previous Eurocode, it was only stress limitation in chapter 7.2 and crack control in 7.3. Then deflection control in the version of 2023 is in chapter 9.3, and the previous version of Eurocode 2, it was in deflection control was handled in 7.4. In the new version, there is a new chapter 9.4, which gives you the control in the serviceability limit state regarding vibration control. In SLS quasi-permanent, long-term effects are regarded, and we are looking now in for the limitations of stress and deflection. The effective modulus of elasticity of concrete can then be taken as 1.05, the mean modulus of elasticity, divided by 1 plus phi, which is the creep coefficient. One can wonder why 1.05? Because the uncertainty on the creep coefficient and the mean modulus of elasticity is much larger than 5%. Of course, the difference comes from the secant modulus of concrete, ECM is ECM, and the tangent modulus of concrete is 1.05 ECM. So that's where the difference is. But it makes, according to me, no use. It's not very sensible to make that difference. As a simplified approach for the calculation of stresses, valid for crack width calculations only, a modular ratio ES over ECM equals to 15 may be used for both permanent and variable loads. So it's only valid for crack width calculations, which I find very strange. And the modular ratio equal to 15, if you do that for both permanent and variable loads, I do not recommend this. I rather prefer to use the modulus of elasticity equals to the secant modulus of elasticity of the concrete divided by 1 plus k times phi, and k is the effect of is the ratio of the effect of the permanent loads divided by the effect of the total loads. By using this, you will see that the more the permanent loads are present, the influence of the creep coefficients gets bigger. So that makes sense. More on this factor K you will find in video 21 on the playlist Concrete Beams 2022 and in video 25 on the playlist Beton 1 2020. Table 9.1 is a table for the verification of stresses and crack width limits for appearance. So this is new. It's only for appearance. And when you look at this table, then you will see that for the calculation of minimum reinforcement according to 9.22, for the minimum reinforcement, there is no crack width limitation. So the only limitation is on the steel stress, and it must be smaller than the yield stress of the steel. So that's Okay. For the verification of crack widths, according to 9.23, we know that this is an SLS and that the limiting value of the crack width now is 0.4 millimeters. Now this is strange. It's something new. Normally we use 0.3 millimeters in all exposure classes, but now we have 0.4 millimeters. This is because we are talking about appearance, not about durability. And the steel stress must be limited to the yield stress of the steel. By verifying the stresses in the reinforcement, and if you when you do that to avoid yielding at SLS, then you calculate in the characteristic combination of actions, and then the steel stress must be smaller than 80% of the yield stress of the steel. It is remarkable that if you compare column 1 by column 2, the calculation of minimum reinforcement, it's also called the minimum reinforcement to avoid yielding, which is exactly the same words as was said here. But the stress limitation here is the yield stress of the steel, and in this case, it's 80% of the yield stress. The first column for the minimum reinforcement, we do not know, is it short-term or is it a long-term calculation? Is it with the creep coefficient equals to 0 or not equal to 0? We don't know. It's not stated. The crack width calculation is always a long-term calculation because it's in quasi-permanent, just by definition. And the other verification in the characteristic combination of action, it is a short-term calculation. Table 9.2 is about verification of stress and cracks with limits for durability. Then you will see that for different exposure classes, you will have different conditions regarding the crack width limitation or the concrete stress limitation. First of all, for reinforced members, you will see that in the combination of SLS characteristic, the concrete compressive stress should be limited to 0.6 FCK. This is strange. Because what about the 0.4 FCK in SLSQ and 0.5 FCK in SLSF of the present Eurocode of 2004? Why is there no limitation in the concrete stress for SLSQ? So I think this is an omission. Secondly, we see that the limiting factor of the crack width, the calculated limiting factor of the crack width, is not just 0.3 millimeters like it was today, but it is 0.3 millimeters multiplied by a factor, a surface factor K. This surface factor is there, it's new, it's completely new. It's the difference between the crack width at the surface and the required mean crack width according to durability. So in fact, the crack width that you calculate at the surface has nothing to do with the real crack width that will appear in practice. Because you have a theoretical value and then you have a characteristic value. So you have a difference between those two. The factor K surface is just indicating, it's just a factor that you can modify your limit value of the crack width at the surface when your concrete cover is bigger than the nominal required concrete cover for durability. So then you can change your limiting factor on the crack width. This factor must be between 1 and 1.5, and it's defined as the actual concrete cover divided by 10 millimeters plus semi-dur, which is, of course, the concrete uh, um, uh, cover required by the environment, but required by durability. So let's I put the attention on the fact that semi-dur here, it's not nominal value. It's really the semi-dur value. Of course, the actual value must be bigger than the nominal value. Otherwise, it makes no sense at all. Let's go deeper into that because this isn't something new. So we have seen now, are the different formulas, and we take two cases. And the first case is of a slab where there is a 35 millimeter carbonation depth in 50 years. So that's what you are designing for. It's a slab for a rooftop and it's cast in situ. And the maximum diameter of steel rebars that we use is 16 millimeters. But the actual concrete cover that we used on site is 50 millimeters. Okay, that's the first case. We know because it's a rooftop exposed to rain and frost, we will take EC4 as durability class, and the exposure resistance class is XRC5 because we have a target of 35 millimeters carbonation depth in 50 years, so we are in XRC5. So semi-dur from the tables equals 30 millimeters. No problem with that. It's cast in situ, so the delta C depth is 10 millimeters. Because it's a slab geometry, we can subtract 5 millimeters from it. So in total, the nominal required concrete cover is 35 millimeters. No problem. The surface factor now is the actual concrete cover on site divided by the semi-dur 30 plus the 10. It's 1.25. It means that the limiting value for the crack width is 0.3 times 1.25. It's 0.375 millimeters. Okay. Now let's take case 2. It's also a slab. We also require a 35 millimeter carbonation depth in 50 years, a maximum of. It's a rooftop, but this time it's prefabricated. It's a prefabricated slabs with a maximum diameter of 16 millimeter, and the actual concrete cover is also 50 millimeters. It's just the same roof slab, but the previous one was in situ, cast in situ, and the second one is prefabricated. It means that we are still in the C4 and in the exposure resistance class XRC5, and semi-dur stays the same, it's 30 millimeters. But because it's prefab, the tolerance on the execution now is 0. And because it's slab, we can subtract 5 millimeters. So C nominal is now 25 millimeters. The surface factor is the actual concrete cover divided by 10 plus semi-dur. So it stays the same, it's 1.25. And the limiting value for the crack width stays the same, it's 0.375 millimeters. Now we have a big problem. If we look now at the rebar and then the surface of the concrete, you will see that the situation is that the actual concrete cover is now 50 millimeters. Okay, that's the same. But in case 1, you will have C nominal. That's the one that the required concrete cover for durability is 35 millimeters, and it corresponds to crack width of W1. And in case 2, it's 25 millimeters C nominal, and the crack width is W2. But for both cases, when you calculate for both cases, the limitation of the crack width is 0.375 millimeters. That we just calculated. Now something is not right, that's for sure, because W1 and W2 do not correspond with 0.375. If you can easily calculate what W2 is. It's 0.90 millimeters, and W1 is 26 millimeters. So this is completely different from the 0.3 millimeters that is required in a normal situation. So in a normal situation, you will have the rebar and you will have in case 1 or in case 2, it doesn't matter, 25 or 35 millimeters, and the maximum crack width must be 0.3 millimeters. That's the goal. If you compare this with this, then you see immediately something is not right. This cannot be correct. So I strongly recommend to use as factor K surface the actual concrete cover divided by the nominal concrete cover. And then you will have a situation where it is logic to use an increase of the limitation factor of the crack width.